Hey there, welcome back to 2241. This is going to be our arc length and curvature video, 2.2. All right, let's get started with our terms as usual. We have to go over reparametrization. So we've covered parametrization. You may have seen arc length in Calculus 2. We'll talk about arc length in general for parametrized curves, what it means to do a unit parametrization, which is usually what reparametrization will be for. We'll have a general idea of what a smooth curve is or looks like. And this is important, curvature, as a measure of something about curves. We'll learn how to compute the tangent, normal, and binormal unit vectors. These will also give us what's called the TNB or Frenet-Serret frame. And then the TNB coordinate planes, which have names, will be generated from this frame. Lastly, we'll have the osculating circle. We'll learn how to find that. And the torsion, which is a similar measurement of a curve to similar to curvature. All right, so let's get into our formulas here. So as usual, our curves will be specified by a vector function with x, y, and z as functions of a single variable t. And then the curve itself will be the output of this function. It's the image. All right, so arc length. What is arc length? Well, you've seen maybe this formula, which I'll write down here, in Calculus 2. It looks something like this. dx. And this is what we would get right here if t was equal to x and we had z equal to 0. We would be parametrizing, or I guess z was constant. We would be parametrizing a planar curve parallel to the xy plane. In this case, we have all of these things as a function of t, and this now allows us to compute the arc length of more general curves. Now, if you simplify this a little bit, or you're a little bit clever, you'll notice that this is the norm of the tangent vector, not the unit tangent vector, just the derivative of r, because we need to take the speed at which the curve is traversed into account here. Okay. Now, the arc length function is a little bit different. It does a similar thing, but it tells us how much arc length there is between a certain point on the curve, chosen by specifying this bottom value of the integral, and another value of t. And so we will integrate this same integrand from the arc length, just with a variable upper bound. And this also gives us that the rate of change, the speed along the curve, is given by this, the speed at which we traverse a single unit on the curve. All right. The unit tangent vector is next. We may have seen this already, but the tangent vector itself is r prime, and then if we want the unit to just tell us the direction, we use our unit vector formula and divide by the norm of this vector. In terms of the arc length parametrization, S, so we can reparameterize in terms of arc length, we have this formula, r prime of S, divide by r prime of S norm, and then times ds dt. So this is a chain rule thing. All right. Next up, we have something fairly important, the curvature. So we can talk about the curvature of space curves and plane curves. This is a special case of space curves, but it is good to know that formula. So the curvature of a space curve is given by the norm, or the rate at which the unit tangent vector changes. This is the amount of change. So you can think maybe if the tangent vector is pointing in this direction and it starts moving in that direction or starts to turn, then the curvature is positive. It's telling us that the tangent vector is changing direction over time. Now, usually it's a little bit easier to compute the curvature in terms of a parametrization that is not arc length. And that is because this arc length parameterization can be difficult or impossible to find by hand sometimes, or often, actually. So this formula can be much easier for us to work with. And then plane curves, this is what happens when you parameterize in terms of x. You say t equals x, and z is a constant. Then you get this formula for curvature. Okay, notice also that it involves the second derivative here. And then up here, we have that t itself is already a derivative of r, and then we take a derivative of it to get curvature. So yes, there is a second derivative happening up here as well. All right. Next up, we've got our unit normal and binormal vectors. The normal vector is the unit vector in the direction of change of the tangent vector. So this is related to the curvature. It's the curvature is the magnitude of the change, and the normal vector is just the direction of change. The binormal vector is just the last thing that we need to finish off our TNB frame. So if you think of T as an x-axis, N as a y-axis, then B as your z-axis. And you get it by looking at the cross product, because that is a vector orthogonal to both T and N, if you remember your vector algebra. The binormal vector is also useful for measuring something called torsion over here. It's a little bit more complicated than curvature, but we'll talk about it on the next page. And it has these formulas. So this is the defining formula. It is this constant right here. You take the derivative of your binormal vector, and that should be proportional to the normal vector, and the magnitude of that proportion is your torsion. There are some other formulas for it here that are a little bit easier to compute. You can take the derivative of the binormal vector dotted with n. You can do this if you have a parameterization that you don't want to do in terms of arc length. You can have this one, and this is a scalar triple product, so it has a nicer interpretation. Oh, and then n prime here is dn dt. That's why we have dt ds over here. And last but not least, we have a property of vectors that allows us to swap or to move the parentheses over to t and n at the cost of swapping the dot and the cross, which then gives us t cross n, and thus b right here, dot n prime. And so this is our final formula for torsion. Okay, so curvature and torsion are both measures of the twistiness of a curve in certain ways, and they'll be important for us later. And here are our objectives. So we have easy, medium, hard. So first off, I just want you to remember some of the formulas in this section. You should be able to compute these formulas for simple curves like planar curves or the helix. And you should understand the geometric significance of a lot of the quantities in here, which just means that you should be able to draw a picture of them that explains what those quantities are. Your medium goals: compute the formulas for more complex curves. These might be things like a conical, what is that called? A conical helix, or maybe like a toroidal spiral or something. You should be able to reparameterize simple curves in terms of arc length. I did say earlier that this is sometimes impossible to do by hand, but for simple things, you should be able to do it. I want you to be able to find equations of T and B planes. So those named planes in the terms, we should be able to find equations of those once we find T, N, and B. All right, our hard objectives are to compute curvature for curves derived from surfaces. Okay, so these are things like the toroidal spiral or the trefoil. And you should be able to derive the equation of an osculating circle for arbitrary curves. This is very difficult, actually. And so it is a hard objective for you here. Okay, so let's move on to our next page. Here we'll go over our terms and have lots of pictures to go along. So reparametrization. So let's say we have a parametrization in terms of t, as usual. So t equals 0, 1, 2, 3, 4. So the curve is going pretty consistently here, and then it speeds up a lot, and then it slows down. And then if we have another variable u that also traces out the same curve, but for different values. So t is increasing here, u is decreasing, and it goes from 5 to 4.2, so it's kind of slow. And then 2.1, it speeds up, 0 to -1 to -6 to -7. So u is moving at different speeds than t, but is tracing out the same curve using a slightly different function. And then u and t will be related by some function here that just tells us how to rewrite our vector functions in terms of u or t. The arc length function, this measures the distance from a particular point chosen on the curve. So given some parameterization t, our arc length is the literal distance from here to here, just in space. If I travel along that curve, how far did I go? Where is it that I've traveled 1 unit? Where is it that I've traveled 2 units of length? 3, 4, 5, 6, 7, 8. And if I've traversed these at different speeds, I need to be careful about how fast things are going so that I don't think, oh, I went from t equals 3 to 4, I only got 1 unit. Well, if I went from there to 4 really quickly, then I could have covered 1, 2, 3 units. The unit parameterization with respect to arc length just means using s as the parameter. And this right here, the arc length function, is how you get that. You just rewrite, or you solve this for t and then rewrite everything in here. A smooth curve is a curve that doesn't really have any cusps, corners, or weirdness with the derivatives. Smooth curves don't do this. So here's a corner, here's a cusp, this part is smooth, this part is smooth, this part is smooth, and then this part is smooth. But right here, there's an issue with the derivative. The derivative of this might not match the derivative of that. Okay. Maybe the second derivative doesn't match, that sort of thing. Okay, so there's our smooth curve. And now curvature for a smooth curve is a measure of how tightly curled a curve is at any point. So you pick a point, curvature depends on where you're looking at, and you think about, okay, how tightly is this thing turning right there? And that's related to the second derivative. So what's happening here is that the curvature is inversely proportional to the radius of the osculating circle, which we'll define in a second. But I've drawn some pictures here to give you an idea. So I have this blue curve in space, and I have a couple of points chosen on it. And I've drawn some circles here that basically match the second derivative of the curve at these points. And the radii of those circles is 1 over the curvature. So it's sort of an inverse radius measurement is what curvature is. So you can think, all right, if the radius is really, really small, then the curvature is very, very large. It's turning very, very tightly. If the radius is really, really large, say even infinite, then the curvature is 0. Well, if the radius if the curvature is 0, the curve is not turning at all, and I have a straight line. And then you can think of the osculating circle as an infinite, a circle with center at infinity. All right, up here, we're going to start talking about our tangent, normal, and binormals. So we have a curve given, and it's being traced out in some direction here. And the tangent, normal, and binormal vectors can be computed. The tangent vector goes in the direction of the curve, of it being traced out, and it's like an x-axis. The normal vector goes perpendicular to that, and it tells us the direction in which the tangent vector is changing. So the tangent vector is going to start moving up and point in that direction. It's like a y-axis. And then the binormal vector tells us the direction in which the normal vector is changing. So it's sort of a twist. So the tangent vector moves up like this, the normal vector is going to move up like this and maybe out a little bit. So it will twist the curve towards us in space. You can think of this part of the curve as being closer to us than this part. And so now I've drawn these 3 vectors. They're all unit vectors. I can think of them like I, j, and k, but they're just sort of moving around through space. So the TNB frame actually depends on the parameter t, little t, I mean. So at this point, t1, you have particular vectors that give you a frame, but then up here later on during the curve, you have these vectors that are slightly different, pointing in different directions, situated differently in space, that give you a different frame, but they are all related to points on this curve and the direction it's being traced out in. Last is the, not last. Next, we have the coordinate planes in the TNB frame. So your Frenet-Serret frames are these 3. You have the normal plane, the rectifying plane, and the osculating plane, and they're all perpendicular to certain vectors. So I've written this out nicely. The normal vector is orthogonal, or sorry, the normal plane, script n, is orthogonal to the tangent vector. And so it's in the plane of the normal and binormal vectors. You can think normal contains both normal and binormal, so normals. The rectifying plane is the one that is orthogonal to the normal vector, and it contains the tangent and binormal vectors. I don't know how you can remember that one. It's the weird one for me. And then last is the osculating plane, and this is the one where the osculating circle lives. So it is orthogonal to the binormal vector. This is the one that is sort of the plane that the curve is almost in. If this was a planar curve, the osculating plane is the one that it's contained in. The osculating circle, well, is contained in the osculating plane that I just mentioned. And it is, again, the circle with radius that is inverse to the curvature at that point. And its second derivative here, parameterized, should match the second derivative of the blue curve at that same point. All right, last up is torsion. So this is a measure of how much the curve is twisting away from the osculating plane at a point. So here's our osculating plane, and the curve is then twisting away from it here. You can see that it's got some distance between it. This is a helix, as it's because the helix is a good measurement of basic measurement of torsion. Okay. And you can think of the torsion as a measure of the tightness of a helix drawn to a curve. So if you have some random curve in the plane, but then you take a point on the curve and you start to match its travel very close to that point, and you use that to draw a helix, however tight that helix is, that's the torsion, to measure how quickly you're moving away from this plane. So if the helix is very, very tightly curled and it spins very quickly in a short amount of time, the torsion is very small. But if the helix is very long, like a stretched out slinky, then the torsion is very large. And the direction of the torsion, if it's curving this way or this way away from the plane, is signed. So it's a measure of what's called the chirality of a curve. It's basically just whether it's right-handed or left-handed spinning. Okay. So those are our terms and our formulas. And in the next video, we'll do some examples, but go ahead and give these a review. Make sure that you're comfortable with some of these formulas, or at least looking at them, you think, all right, I can compute these if I needed to. And then go to the next video and watch the worked examples.